Hello there and welcome to the series of videos going through the content of A-Level Maths. Here we're looking at hypothesis testing with the normal distribution so we can answer questions from exercise 3G. So imagine that we had the set of data that goes as follows: 1, 2, 3, 4, 4, 5, 5, 6, 6, 6, 7, 7, 8, 8, 9, 10 and 11. For this data the information is as follows. It's normally distributed with a mean of 6 and a standard deviation of 2.65. So that's the summary data for this data set. Then a mean of 6 and a standard deviation of 2.65. In this case, the data set is so small that we can include all the data. In more practical situations, we would most likely take a sample of the population. We need to consider how this would affect our use of the mean and the variance. Now, if we were to take a sample of just size 2, for example, you'd probably want to take more than that, but just for this simple case here, a random sample of 2 data points here. Let's say the first one was 4 for the first pick and the second one was 5. That mean would be 4.5. Our next two picks would be 3 and 9, so that mean would be 6. The next two picks would be 6 and 5, the mean there would be 5.5. The next two picks would be 2 and 8, so the mean there would be 5. The next two picks are 7 and 10, so we've got 8.5 as the mean there. And the next two picks are 6 and 8, so the mean would be 7 there. So what we're going to now look at is the summary for this set of data here, the summary of the sample means. Let's now calculate the mean and the variance of this set of data. So in this case here, the mean, the sample mean, the mean of these samples of data is going to be, effectively the mean of the means is a 6.08, and the standard deviation, or the variance rather, is going to be 1.78. That's how far these means are spread out. In that case, the standard deviation is going to be 1.33. So what we've done there is we've worked out that for this data set where we pick two data values at random from our data set, is that the means are normally distributed with a mean of 6.08 and a standard deviation of 1.33. This is effectively the normal distribution for the means, not the normal distribution for the data set, the normal distribution for the means when we pick two data values from the data set. So it's the normal distribution of the sample means. Okay, and when you've got the notation for this sample, you put an X bar on the top of your X there. Okay, so if we were to take enough samples, then because the data is normally distributed, the sample mean will average out to be the same as the population mean. So we would expect naturally that this 6 here and this 6.08 here would be pretty close to each other, if not identical to each other. However, how is the variance affected? Well, in this case here, we can see it's gone from 2.65 to 1.33. Remember that 1.33 is not representing the variance of the data set, it's representing the variance of these means. Okay, so when choosing only two values from our sample, consider the range of possible means. So the smallest possible mean would be 1.5 when we pick the values 1 and 2, and the highest possible value for the mean would be 10.5. So when we have a sample size of 2, the mean can range from 1.5 up to 10.5, so quite a big range there. But when we take a sample size of, say, 10 values from this data set and we work out the mean there, then the sample size of the mean will range from 4.2 to 7.8 when we take the mean of those 10 values. So we can see here, the smaller the number of sample that we pick, the higher the potential range of means is going to be. So therefore what we want to say there is, the key idea to take away from this is that with a larger sample size, like this thing here, the range of possible values is going to be lower, only from 4.2 to 7.8, rather than 1.5 up to 10.5. Hence the variance is always going to be lower as there is a smaller range of values to exist in. When dealing with a sample, the variance is estimated by dividing the population variance by the size of the sample. That way, a larger sample will have a smaller estimated value for the variance. Okay, so what we're going to do then is for the variance for how the means change, for the variance of the means in a sample, we divide it by n. So this is the conversion from our data set to the data set for our sample means, where the sample size is size n. So you can see that the bigger n is going to be, the smaller this number is going to be in total, because we're dividing by more, and the smaller the sample is, say if the sample size is just 2, we're not dividing by very much, so the variance of that sample is going to be quite big. So you use the population mean straight away, and you divide the population variance by the sample size. I'll show you where this is going to come in a second, but this is a key conversion for when you start to do an hypothesis test on your data. Okay, let's get stuck into a question then and see what on earth we've been talking about so far. A company sells fruit juice containers. The amount of juice in a carton has a normal distribution with a standard deviation of 3 milliliters. The company claims that the mean amount of juice per carton mu is 60 milliliters. A trading inspector has received complaints that the company is overstating the amount of juice per carton and wishes to investigate this complaint. The inspector takes a random sample of 16 cartons and finds that the mean amount of juice per carton is 59.1. Using a 5% significance level and stating your hypothesis clearly, test whether or not there is sufficient evidence to uphold the complaints. So, let's go through the stages for a standard hypothesis test. First of all, you need to write out your hypothesis. Now, the null hypothesis is always that the mean is equal to something. In this case here, the mean should be equal to 60. The alternative hypothesis in this case, given that the inspector observes 59.1, is that the mean is lower than 60. Step 2 is to convert the population distribution to the sample distribution. So in this case here, we're now going to be working with this distribution here. So in this case here, this was the population distribution, fine, but what we're going to use in our hypothesis test here is that the sample of the means, because what they've done here is they've taken a sample of 16, so we need to use the sample distribution to compare the inspector's sample with. So in this case here, it's a mean of 60 and then a variance of 3 squared over 16. That's a standard deviation of 3 over the square root of 16. So now that we've got our suitable sample distribution, now we're using the sample distribution, we need to find the probability that a random sample of 16 gives a mean equal to or lower than 59.1. So what we're going to do then is we're going to use our calculators. The mean is going to be 60, 59.1 is on this side here, and we want to know what area this is going to be. Now, depending upon whether this comes out at more than 5% or less than 5% will depend on what hypothesis we accept and reject. Bear in mind here, this is the key part of this question. This is always the bit that people forget about and that it accidentally goes wrong on. Your standard deviation is now going to be 3 divided by the square root of 16. I would write this actually as 3 divided by the square root of 16. So it's the original sample, it's the original standard deviation, but then you divide it by the square root of your sample size. Now when we plug this into the calculator, the probability that the mean is less than 59.1 is equal to 11.51%. Now that's still quite a high probability that the mean is going to be less than 59.1%. If you take 10 samples of 16, you're probably going to find one that is less than 59.1. So therefore, what we say to the 5% significance level is that although getting in this range is unlikely, it is not below 5%. Therefore, it is not unlikely enough for us to reject the null hypothesis that the mean is actually 60. So we are going to accept the null hypothesis here that the mean is 60. 11.5% was higher than 5%. So therefore, we accept H0. Now, if this probability came out to be something like 1.3%, that is a really small probability. The inspector would then be suspicious that the juice company is providing juice of less than 60 millilitres as a mean, so therefore they would reject the null hypothesis and accept the alternate hypothesis. That's if the percentage that came out here would be less than 5%. In this case, it's more than 5%. There is a very high probability that this could just have happened by chance, so therefore we'll say that the mean is still 60. Another type of question would be something along the lines of a critical value type question. So just a reminder about your Z values. There's another way of doing this, I'll show you that at the end, but there's another way we can use these Z values here. So the Z values, remember, is equal to x minus the mean divided by the standard deviation. That's for the population, we've already seen that, but when you're working with a sample, remember, your variance has now changed, so that when you work out your Z value, it's just going to be the square root of your variance. So it's going to be sigma over the n square rooted. So let's see how we can use this inside a question. This is just what I've explained here. So using this inner question here, a machine produces bolts of diameter d, where d has a normal distribution with mean 0.580 and a standard deviation of 0.015 centimeters. This machine is serviced, and after the service, a random sample of 50 bolts for the next production is taken to see if the mean diameter of the bolts has changed from 0.580. The distribution of the bolts after the service is still normal and a standard deviation of 0.015. Find at the 1% significance level the critical value for this test, stating your hypothesis clearly. So, remember that the critical region is the region where the null hypothesis would be rejected. We would start to be suspicious in that critical region. So, the null hypothesis is always a mean is equal to something, so in this case here the mean will stay at 0.580 after the servicing. The alternative hypothesis is that the mean will not be the same as 0.580 after the servicing. We need to convert next the population distribution into the sample mean distribution, so in that case the mean stays the same, but the variance changes. It's now 0.015 squared over the square root of 50. Now, using the sample distribution, we need to find the regions that have a probability of less than 1%, or a total area of 0.1%. Now, what we're going to have to do there is we're going to have to divide up our tails into 0.005 probability in each tail. Now, one way of doing this, the first probably way that I would do this is actually I'd use the inverse normal mode on my calculator, but let's just show you a question where we do use this conversion to Z values. It will be worthwhile going ahead and doing that. So on the standard normal distribution, where the mean is 0 and the standard deviation is 1, we could look up in our standard results in the formula booklet, and we know that the Z value at this point here would be 2.5758. Symmetrically, it would be minus 2.5758 on the left-hand side. And then when we convert back from 2.5758 back to this value here, we're going to use this conversion here. So the Z value in this case, this is the Z distribution, this is the X distribution, 2.5758 will be on the left. The D value we don't know, but we do know the mean and we do know the sample variance, the sample distribution, the sample standard deviation rather. Got there in the end. So we know the sample standard deviation. We know the mean, so let's just rearrange both of those onto the other side, and we get 0.5854 as the x value appearing in this spot here. And symmetrically, it must be the case that it's going to be minus 0.58. Oh no, wait, no, it's not symmetric, is it? Because we've got this value here. It's going to be 0.5745 on that side there. Now what we're effectively saying is then that the critical region is going to be in this region here or in this region here. So it's where the sample means are going to be less than or equal to 0.575 or more than 0.585. So there we are, that's the answer to the question. That is the critical region for this question here then. Part B is that the mean diameter of a sample of 50 bolts was found to be 0.587. Comment on this in light of the critical region. Well, since this mean is inside the critical region, there is sufficient evidence to reject the null hypothesis. That would mean that effectively after the servicing of the machine, the diameter of the bolts has now changed. Okay, your turn to have a go at this question here then. Pause the video and try this question out. Right then, let's get started on this question then. So the IQ scores of a population are normally distributed with a mean of 100 and a standard deviation of 15. A psychologist wishes to test the theory that eating chocolate before sitting an IQ test improves your score. A random sample of 80 people are selected and they each are given an identical bar of chocolate to eat before taking an IQ test. Part A is find at the 2.5 significance level the critical region for this test, stating your hypothesis clearly. Okay, well let's get started on those hypotheses then while we remember. So the initial hypothesis is that the mean is equal to something. It's always the initial one that's where the mean is equal to something, in this case 100. For the alternate hypothesis, we're going to try and predict that the mean will increase after eating a bar of chocolate. And the x distribution is a normal distribution where the mean is 15. Now this is the sample distribution here, so it's x bar squiggly n open bracket, mean will be 100 and the standard deviation will be 15 over the square root of 80 squared close bracket. So this here is the sample, this is the standard deviation for the sample, for all the samples. Okay, so let's now try and think about what we're trying to work out here. We're trying to work out the critical value, so we're working out this value down here, at which point we would have an area of 0.025 when the mean is 100 and the standard deviation is 15 over the square root of 80. So let's go to the inverse normal mode in our calculator. Now remember that it's the area on the left that you need to type into the area bit, so it's going to be 0.975. The standard deviation I just typed in as 15 divided by square root of 80. Type that straight in and it will calculate 1.677. Try it and see if it works on yours as well. And the mean here is 100. So the answer to this question here, this point here, is going to be 103.3 to 4 significant figures. So that is the critical point. So therefore the critical region is going to be x is bigger than, or x bar is going to be bigger than 103.3. So that's the answer to part A then. The mean score on the test of a sample of 80 people was recorded at 102.5. Comment on this observation in light of the critical region. So in this case here, 102.5 is not in the critical region. It's not in the critical region. So we're going to have to say something about the hypothesis and something about the conclusion, linking it back to the question here. So it's not in the critical region. I'll just finish off by saying this last bit here. So it's not in the critical region, therefore there is not enough evidence to reject the null hypothesis, or you could alternatively say accept the null hypothesis. In terms of the context of the question, you would write something along the lines of, it appears that chocolate does not improve the IQ test score of a sample of 80 people. Okay, so there we are. That's the answer to this question then. So have a go at plenty of the questions from exercise 3G. Have a go at the problem-solving ones, the exam-style questions, and ask your teacher for help if you need any. Great, thanks very much for watching.